It's been good.
Yeah, that's good to hear.
Yeah.
I'm just setting up my screen right now. Any updates or anything to talk about?
Well, my final is tomorrow morning.
Yeah, is that why we scheduled 2 tonight?
Yeah, I want
Makes
to be
sense.
extra prepared.
Yeah, makes sense. Sorry, you told me, what time did you say it was? In the morning?
In the morning, so like
Oh, okay.
8:45.
And that's your first one?
Yeah.
Okay. Well, you know what to do, right? I gotta say it. You gotta make sure, obviously, get enough sleep. But if you gotta, usually breakfast, you know those things, right?
Yeah.
It can really make a big difference, honestly. And try not to study. Try not to look at your notes. I know that might seem counterintuitive, but like if you don't know it tomorrow morning, you're not going to know it, But
Yeah.
if you said you felt you did well on your other test, and I don't know how your other ones went, but from my perspective, it seems like that you do know what we've talked about, and I think you're going to do fine. So hopefully that's an encouraging pep talk for you. All right, so you want to leave off let's see, where we left off last night. Let's see. Okay, should be sharing. There we go. I can't hear you if you're speaking. Are you there?
Yes.
Oh, okay, cool. So yeah, did you want to start off where we left off last night? Or did you want to
Um,
go over any of those things? We did the conversion on units. We got into Newton's laws, I believe. I gotta look. Or maybe we just did, yeah, kinematics. That's what we got on.
mhm.
So you want to start, you want to go, I think, oh yeah, we kind of sped through the third problem on motion, on kinematics. But we can do that again, or go over any of that. Otherwise, we can go on to forces in motion.
Could we go over um some of like the conversions, please?
Yeah, of course. Let's do, since we did these, unless you are opposed to it, let's do a new one that's not on the paper, unless you really want to do that. But I always am a believer that it's good to do different things, right? So let's just 50 kilometers to, let's make it not too bad so far. Millimeters. How many kilometers? How much is this?
Okay. Let's see.
Are you working on this one?
Yes.
Okay.
Is it 50 million millimeters?
Yes. Yes. And so how did you do it? Did you go like this? Where this is kind of the standard thing that you always want to do if you don't know the conversion factor. And so, okay, how to get to meters, right? And there's 1,000 meters. We're canceling kilometers. That's why it's on the bottom. Or did you say, 1 kilometer is equal to 10 to the 6th millimeters, or neither?
I think I did something similar to the second
This one?
solution. I found the like metric ladder and then I just counted 6 faces.
Okay, good. Exactly. That's exactly how you should do it. Yeah. Because you can see that it's 3 away from meters and then 3 away on the other side from meters, exactly on your ladder. Great. Because that's the easier way to do it. You can always do this, right? And you have to sometimes like parsecs to inches, but it's definitely better if you can use your metric ladder. Is that what you called it?
Yeah.
Yeah, that's a good one. Okay, great. So then looks like you guys do this. So let's have like something weird like, oh yeah, and so 50 million kilometers or 50 million millimeters. How do I write that in scientific notation? The most correct way, because it looks like he does want you to have that down as well.
So that would be, is it 5.0 times 10 to the 6th?
10 to the 7th, right? Right? Because you
Oh,
got to,
yeah.
yeah, okay, because you got to move that thing over, and you're adding an extra 10, right?
Yeah, okay.
And you know, he might take a point off. I mean, it sounds like he will if you did this one, right? Of course, these things are equal for the reasons we just talked about. Okay, so now let's do something a little harder. How about this one? Nanometers to meters. What do you think? Unless you want me to walk you through it, just let me know. Otherwise, I'll just come up with problems for you.
Okay. So for the like first conversion, I got 0.06250 meters.
That one.
Yeah.
Okay. Did you remember to do? This is actually, since it's n, it's nano, right? Which is 10 to the negative 9th. So you did that one.
Yes.
Okay. If we did, then it should be, we would move it to the right. Here's our decibel for that, right? And we go 1, 2, 3. And so it should be 6.250 times 10 to the negative 6th meters. Your answer would be 6.250 times 10 to the negative 2. So
Oh,
I'm
okay.
not sure if you did it twice. I'm not sure how you got this one. Maybe you used micrometers. She said you did use the 10 to the negative 9th. So since I can't see your work, I'm not sure where you made a mistake, but does this make sense? Not that one.
I'm still a little confused.
Okay, so if we do, this is the original 6 to 50 nanometers. Well, we know that you look at your metric ladder, or just remember that this is nano, which is equivalent to 10 to the negative ninth. So this says, oh, this must be 6250 times 10 to the negative ninth meters. How's that step right there for you?
So if I can use this like half sheet of formulas and stuff like that.
Mhm.
So on that, like I was just doing like the steps up and down to find it. So
So
it just
um,
yeah.
so the nano is 9 steps below meters then, right? That's what that means. So if you have meters and this is your
Oh yeah.
ground
Okay.
level, it'd be 9 steps all the way. 9 steps below the ladder, right? Because it's,
Oh, okay.
and so that's like the basic easy part. And then you also want to convert it to the standard, well, 6.250, right?
Hmm.
But if we have the decimal here at first, well, we're going to go to the right. I'm sorry, we're going to the left 3. So going to the left 3 decimals is basically going up 3 on the ladder, right? Leaving us with
Hmm.
10 to the negative 6th. Meters, yes. Good on that?
Yeah, that makes more sense.
Okay. And so let's do one of these more where you have the conversion factors, more of them, right? So since you
Okay.
did parsecs before, so how about you get this one to feet?
Okay.
Still working on it.
Okay. So I got 1.27 times 10 to the 18th feet.
Okay. Divided by 12. Okay, that sounds like it's right. I got to put it in. I should have put it in. But hopefully you did. I want to show you the work as well, and hopefully you did something like this to get these right. These are all of your conversion factors to things that you know. And so now, oh, the thing should be in feet. So I'm not going to do calculator, just do Google. What did you say, 1.2 something?
1.72.
Okay, that's exactly, yeah, you got it right. Awesome. And so that's good because that's the more difficult one, honestly. But maybe it sounds like that ladder and getting familiar with that maybe is more you're having trouble with that, or maybe just a little practice probably, and you'll be okay.
Yeah, I think I just need to brush up on it because I haven't seen that in a couple months.
Oh yeah, that makes sense. That makes sense. Okay, let's do a few others and a quick one if you want to spend some more time on it.
Okay.
Okay, so how about quick? How about 56 millimeters to nanometers? How's that?
Okay. Millimeters to nanometers.
So yeah, how many steps do you need? And are you going up or down, right?
You're going up, and is it 4 steps?
It's down actually because millimeters are bigger than nanometers, right?
Oh, to nanometers. Okay.
Yeah, sorry if that wasn't clear. Yeah, good.
Yeah, so down 2 steps?
6 steps. And the reason we know is that milli is 10 to the negative 3 and nano is 10 to the negative 9th, right?
Mm-hmm.
And so that's going down 6 steps. So it'd be 56 times 10 to the negative 6th nanometers. I'm sorry. Millimeters to nanometers. So we are going down, but that means, I'm not sure. Okay. It's 10 to the 6th positive, right?
Mm-hmm.
I got myself backwards. Sorry. Ignore the last 30 seconds. It's definitely 10 to the negative 6th because we went down. We went from 10 to the negative 3 meters, right? Sorry. I don't, maybe that's why you're not thinking about it, because that's how I've been doing it. And that's how I always think about it, right? What's a nanometer? 10 to the negative 9th meters, right?
Mm-hmm.
But if you have your ladder, then of course here's meters, and then 1, 2, 3 down to millimeters, right? Just as going up 1, 2, 3 is kilometers. And then, well, if I go down 3 here, it's micrometers, right? And then another 3, 7, 8, 9 is nanometers down.
Oh, okay.
So if this is true, what about 760 micrometers to millimeters?
It's 3 steps up.
Yeah, exactly. So then what's the final thing look like? Or at least the intermediate step, not the final scientific notation answer, maybe, unless you can. What would you write down as your answer?
Um, 0.760.
Yes, exactly. Which, yes.
Okay.
So this one, I don't know what is wrong with it, but this is definitely 10 to the 6th, right? Since we went down just as you went, like there's a lot more meters in a kilometer, right? There's 1,000 meters in a kilometer, right? And you're going up the ladder to get from meters to kilometers. And so that means you're going to have a positive number if you're going from a larger one to a smaller one. And since millimeters is definitely larger than nanometers, as you go down the ladder, that's going to give you a positive value up here, 10 to the 6th for millimeters to nanometers.
Okay.
And then as you go up the ladder, it's a negative number. And of course, that's the case because if I go from nanometers to meters, well, it's 10 to the 9th, right? 10 to the negative 9th. Because 1 nanometer is 10 to the negative 9th meters. So that's the way. I haven't used the metric ladder, but it is a really good tool to use. That's why I was getting confused, but I got it now. So hopefully that makes sense. As you go up, you want to have a negative on your scientific notation.
Okay.
And then of course, as you did it here, you did it correctly. We're going from a smaller one to a larger one. And so what you did was, well, you moved your decimal point, which is the same as saying times 10 to the negative 3, right? Because the decimal place moved 1, 2, 3. That's what you did here.
Okay.
Okay, sorry for the confusion. Do you want to do another ladder one, or do you want to do like you have MPH to meters per second here, or you could, we'll have something different, obviously, miles maybe.
If we could do a problem of miles per hour
Yeah, sure.
to meters per second or something.
Yeah, that makes sense that it might be on there actually, because that's a pretty common one. So let's do like the speed of a plane, right? MPH to meters per second. And you want me to just walk through this one? Show you rather?
Yes, please.
So we want to write, this is the first step when we go by MPH divided by 1. And then like I did last night, I like to write this actually as well, because I don't like that. I want to see what the units are. And it's miles up here, and then 1 hour. MPH is miles per hour. If I know that I want to go to meters per second, right? Well, I need to go from miles to meters and then hours to seconds. But let's do one at a time, right? Miles to meters. Well, I don't know that conversion factor, but I do know that there is 5,280 feet in 1 mile. That's great because I know how many feet are in a meter. And since I want to go 2 meters, I want to go from feet to meters. My feet will be on the bottom, meters up top. And then the last one, so if we want to check ourselves, we say, oh, okay, now I'm in meters. Once I perform the numbers, right? Now I'm in meters. And then, well, hours to seconds, hours is in the bottom now. So my hours better be on top here, and I'm going to seconds. And I know there's 3,600 seconds in an hour. I have no problem doing that, but your instructor may want you to say, oh, that's true, but do this instead, where there's 60 minutes in an hour, and then convert again to minutes per 60 seconds per minute. But notice, of course, it's the same because 60 times 60 is 3,600, right? So you should, hopefully he'll let you easily go from hours to seconds. And then we do it and just put it in. MPH to, we got 700, so 313. Sounds right. Is that what you got? Divided by 3.28, 3,600. Cancel, of course, to make sure you're doing it right and all the steps are okay. But I believe this is the one that you're going to have to remember, that conversion factor, which if you're going
Mhm.
the other way, would be written like this, right? Say you want to go from feet to meters. I'm sorry, from meters to feet, then you would use this one, right? Because whatever is
Mhm.
being canceled is what you want to remember. Um, yeah, because I'm not sure if it's on your sheet or whatever, but and assuming, of course, you remember, that. Oops. Assuming you remember that, there's 5,280 feet in a mile and all that, and the 60 seconds, which shouldn't be a problem, hopefully. So how do you feel about that now? Do you want to maybe you want to do a practice one on your own, or I could just kind of give you a few in an email afterwards, unless you want some feedback right now to make sure it's really you really got it.
Can we do another one right now, please?
Yeah, sure. And in the same thing where I just walk you through, or do you want to work on this one?
Can I try it on my own, please?
Yeah, of course. Let's try going the other way, unless you wanted to keep it the exact same and go from miles per hour. Let's not go crazy yet. Let's do that. So let's do just 50 miles per hour, right, to meters per second.
Okay.
Go ahead.
Um, I got 22.3 meters per second.
Let's see, what is it? 50? Okay, that sounds pretty close. Yeah, perfect. 22.35. And you're okay with the process and everything?
Um, so the first time when I put it in the calculator, I did the whole top row and I multiplied it like all the way through.
Mhm.
And then I got my answer for the top part and then I divided it by the all the numbers on the bottom, like multiplied together.
Yeah.
And then are you not supposed to do that? Because when I got the 22.3, I multiplied the top and then I divided all the way through the bottom.
Yeah, you got to use those parentheses, I think, then on there, because I'm always wary of that, like we were talking about last night. And if you do this set of operations in your calculator, you will get it. But because believe the first thing you said, what you're talking about, you did this. Is that what you said you did? Right?
Yeah.
Without parentheses. And so a calculator, sorry, I get make it. not consistent at all. And so what the calculator is seeing when it sees that, it says, or it thinks that you want this. Remember that you can move around anything like that. That's what it thinks. So that's why you gotta be so careful with these calculators.
Oh, okay.
Now, you can either you can either do like I said with the parentheses, and that'll take care of it because of PEMDAS. The calculator always follows PEMDAS. It'll do what's in the parentheses first, right? So that means that,
Mm-hmm.
and then it'll divide for you. So that's one option. And then the other option is to say 50, you can always multiply, feel free to always do that. But then I do it one at a time and I say, oh, okay, I do that equal sign, do all that, and then divide whatever that result is by whatever else I have to divide by, right? 3,600. And that'll give you
Okay.
obviously the same answer as this, which is the most correct one. But so does that give you some clarity, hopefully? Do you want to do another one
Yeah.
to practice that?
Yeah.
That's a good idea, I think. So let's go like let's do it backwards. Let's go meters per second to mph. So let's do a small one, small in there, so that. Still working on it?
Yeah. Okay, I'm not sure if this is right, but 38.01.
You got it. 30, that's fine. That's good enough. Google says 38.03, but they might be just directly using more significant digits. So that's great. That's perfect. Did you make the same error in the calculator, or did you do it right the first time? With the division, I mean.
Oh, I did it right the first time.
Good. That's good to hear. So yeah, it sounds like you're getting it now. This is also the conversion factor. I don't know if you can just use that one. Obviously, it makes the problem much simpler, right? Just like using your ladder, or just how what is it? 3.28 feet is equal to whatever 1 meter. And so, if you have 20 feet, well, all I got to do is multiply that by 20 to get meters. So I don't know if you can use that conversion factor to go from mph to meters per second, if he'll let you. But don't worry if you don't remember it. Also, there's a lot. You got enough to remember.
Okay.
So yeah, how do you feel more confident in the conversions?
Oh yeah, I think so.
Okay, that is good to hear. Yeah, I can still send you a few if you want to do some practice afterwards, or
Okay.
tomorrow before the thing, an email. So we can make up for a few more minutes as well since I sent that link. So do you want to just go down the list here to motion again, or do you have something in mind? You should probably study like your weakest thing, or at least that's what you and I should go over. The thing you think you feel like you need the most help on.
I would say my weakest part is forces in motion.
Mhm.
Yeah.
Okay. So let's do. It looks like these problems haven't been done yet, so that's a good thing. But there's a problem right there. Yeah, this determine the weight of an 88.02 astronaut. Okay, cool. So this one, we extract the information as always. That's the best thing we can do anytime. And so determine the weight. So right away they give us, oh, weight. That's what you want. Remember, weight is a force, typically m times g, where g is the gravitational acceleration of the planet, right?
Mhm.
And we know that on Earth, we know that value, but this is not Earth because it's a different planet. So we don't know what that is. But we can use Newton's law of gravitation. But I'm actually getting ahead of myself. I'm not even following my own instructions. But we do know a few things here. So we know the mass one, we'll call it, of the astronaut, right, is 88.02. We want to make sure we want to keep all of the digits here. Standing at sea level on a planet. So that's good because we know that they're not in the air. So we're not going to use that other equation. We can just use the standard equation after we write down this other stuff. The mass of the planet, m2, mp maybe, but maybe just stick to m2. I think that's what you've been using, mostly m1 and m2. And then, and a radius of whatever that is, which we can write that down as well. Let's do it for consistency. And our units are meters. And so if everything is in kilograms, good, and meters, we know that we can use the value of G, big G, here would be 7 times 10 to the negative 11th. And of course, the equation that relates all these things. Now, even if you weren't sure of the equation before and you said, oh, I don't know what equation it is, you know that, well, M1, M2, and R, I'm sorry, you use D, distance. Are in that universal law of gravitation, which is little fg, big G, m1, m2, divided by d squared, distance between the two objects. That's what it always is. If you're not sure that this is the right equation, then do the second step, which is drawing a picture. And you say, oh, okay, I have a planet. I don't have two planets. That's kind of weird, but that's all right. It has a radius. Okay, that's the radius of the planet. D, some mass, okay, I don't really care, but there's a person standing on the planet. That's the key insight here. That's why I use the universal law of gravitation
Mhm.
with M2 here. Because it's from the center of one body to the center of another. Even if it's a fly, that little fly still has a center, or this astronaut, obviously it's much smaller than the planet, but it still definitely has a center. And that's what that D is, because that's the only time you can use this equation is when your the distance is from the center of both of the objects. And then that's the rationale and all the stuff. And now you plug in the numbers. So if you want to do that, I won't write them down so you get a chance to practice putting in the calculator and all that. Did you get a thing yet? An answer?
I'm still plugging it into the equation.
Okay, me too. Square. Okay.
Okay, I got 786.3 newtons.
And that's good. I don't know if you did it on purpose, but you use the exact correct number of significant figures too. Maybe you were paying attention. It's okay if not, but we have 4 here, so we have to use 4, right, in the final. And that's exactly right. Is that process okay with you? Were you okay with that walkthrough? Does it make sense? Okay, good. A little additional thing, he might, oftentimes in physics, you have to solve for something, but that's not the final answer. They want you to use what you have here to go actually get the final answer. And so an example you might see, depending on basically how difficult he makes it in general. But remember how we said that weight is mg? That's still true. That's always true. It's just like I said, it's not g of Earth, it's g of this planet. And so a secondary question after you've done this work might be, what is the value of g on the planet? Does that make sense?
Mm-hmm.
And so we know this is the weight. This FG is the gravitational force between them, but it's also the weight. That's the key insight here too into actually using this equation, because it's not asking for FG, it's actually asking for the weight. But I actually forgot to mention that, but we know that the weight actually is the gravitational force between them. And so if they ask you the value of G on the planet, well, then you just have to say W divided by M is equal to G for the planet, right? Where this is the weight. So 786.3 divided by its mass, 88.02. Just as an aside there.
Okay.
But I do want to go back, and this is a key insight here that, like I said, they're asking for the weight, but then, well, that's weird. That doesn't look like weight. Does that make sense? That connection there?
The connection between kilograms and meters?
Between weight and the
Oh.
FG, the gravitational force.
Oh yeah.
Okay, good. Because this picture is really why also. And since they're standing on the surface of the planet, which it says, well, that's why it's the weight, you know. Okay, good. Yeah, let's do. You want to do another one of those real quick, see if we can fit it in? Yeah.
Okay.
Okay. That's a good problem because there's a lot going on there. You see weight, and you're like, oh, I know what that is. That's mg. You're like, not in this one. It's not, right? So I would really know that one, because that one, I wouldn't be surprised if that one showed up. They like to have little kind of tricky ones like that. But let's just do a standard one. Okay, here we go. Okay, if the weight of a person is, how about, they're a big boy, so is that, and they weigh, and they have mass. Okay, yeah, and they have mass of 85 kg. What is the mass of the planet? These planets are very big, so how about 5.8 times 10 to the 7th meters? Yeah, seems okay. So, yeah, do you want to, I can walk through this one real quick, or you can do it, kind of talk me through it, or do it on your paper, you know? Which one do you
Okay.
want to do?
Could I talk you through it?
Yeah. Tell me how to do this one.
Okay, so mass one is 85 kilograms. You don't know mass two.
Agreed.
Your distance is 5.8 times 10 to the 7th meters. The force of gravity is 950 newtons.
That's the key.
And
This is the key
then,
here, newtons.
oh, 950 newtons.
Yeah, sorry, I was, yeah, I forgot to write it down, but in general, yeah. Newtons is, that's how we know it's the force. Anything else?
And then G is 6.67 times 10 to the negative 11.
I have an equation for these, for all this?
FG equals G M1 M.
Sorry. And so which one are we solving for?
And then you're solving for M2, so you need to isolate M2. So you multiply D squared to both sides and you get D squared times FG equals GM1 M2.
Good. What's next? If we're solving, we're still solving for the same, right? M2.
And then you have to get M2 by itself.
How do we do that?
You divide by GM1.
Yes. Sides, right? Because when we cancel, it goes away. And then, of course, we can plug in the numbers. And I got this big old number. So 10 to the 26, and we know it's in kilograms. And we say to ourselves, is that right? Or is it reasonable? We don't know if it's exactly right, but we know it's reasonable because the mass of the Earth is around there, right? So we know that we did it right, and our calculations are good. Even though it's a giant number, it should be because it's a planet. So a little mental check. Okay, yeah, so that's it for this one. And then I guess I'll see you at 7. If you want to use the same link here, I can send it again, but it's just the same link.
Okay.
And be sure to upload any other questions that you have or any other papers. But if you want to just finish or keep working on what you sent before, that's fine too.
Okay.
Okay, thanks. See you then.
Thank you.
Mhm.